features of Datastage is its parallelism, that it can execute jobs in parallel, divide data into multiple partitions, and whatever backend processes are taking place into multiple sub processors, and can execute the job faster. So where do we define this parallelism? How does it know how many nodes are there, how many partitions it needs to create? So this is where we need the configuration file. So a configuration file, basically a user can define a configuration file in Datastage Designer itself. In the configuration file, we specify how many nodes we want the job to run on. We describe the resources that are associated with these nodes, and accordingly, when we design the Datastage job and compile it and run it, it will use this configuration file. Datastage will use this configuration file to understand how the system resources should be distributed and will execute the job accordingly. So this is how a configuration file looks like. It can be, we'll see it in the Datastage Designer, so it will be easier to see there. This is basically in the Unix box. The extension of the configuration file is always .apt, and there is a default configuration file when Datastage is installed. So by default, when we are installing Datastage, default.apt, that is the configuration file that will get created. Now, basically the information that this configuration file contains, it contains the processing nodes, the number of processing nodes. The number of the nodes will determine the degree of parallelism. So it's 1:1. So if we have 2 nodes, then there will be 2 partitions. And if there are 4 nodes, there will be 4 partitions that will be created. So that simply determines the degree of parallelism by the number of nodes that we define in this configuration file. Now, each processing node has its own resources that can be allocated to that node. Now, the main advantage basically of having a configuration file is that the system resources might change from one project to another project, or probably there's an upgrade on the environment that happens and the environment system resources get changed. So in that case, we do not need to go and change the Datastage code. We can simply update the configuration file, and that can be used for that job or for that project, the default configuration file. And that is the only change that we will need to make. We will not need to go and change the Datastage code. So that is one very big advantage of having a configuration file. The configuration file is simply like a text file. So it simply needs the information to be typed in. It's a simple text file with the extension of .apt. It is stored on the Datastage server, and we can edit it. We can edit in the Datastage Designer itself. We can go and create new files or edit the already existing files. Now, by default, when we install Datastage, a default configuration file needs to be defined. So that configuration file is called default.apt. And there's an environment variable that refers to the configuration file which we want the job to be run on. So there are two things. This default.apt will be defined at a project level. When Datastage is installed, we can define it for each project. So that is at the project level. That can be overridden at the job level. So we can define that one Datastage job I want to run on 2 nodes. Another Datastage job, probably it has larger processing, and I want to run it on 4 nodes. So different jobs can be run on different configuration files. Even the same job, I can update the configuration file for the same job as well. So when I want to override that default.apt file, I want to define another file, configuration file, then I have to use this environment variable, apt config file, included in my job parameters, and I can point it to the configuration file that I want to use for that job. So this property can be overridden at the job level itself. Now, if we see the structure of the configuration file, we'll see that there are many elements in it. We have the node name. We have the fast node name is the number of logical nodes that defines the number of partitions. Then we have for each node name, we'll have a fast name. We'll have some pools defined, and we have some resources allocated to these nodes. So we'll see what each one means. So node name is basically any username. So it's not the physical name, it's not the network name. It is a user defined name for any logical node, a logical processing node. Now, fast name is basically the computer system name. So it is referred to as if it's a multi-CPU system, then how that node is referred by the fastest network on the system. So if it is an SMP, that is a symmetric multiprocessing system that has a single CPU, the fast names for all the nodes will be the same. But the node name will be different because node name is nothing but a logical name. It's a user-defined name, and these are logical nodes. The fast name is a physical kind of node. So that would be the same on an SMP system. When we have a cluster system or an MPP system where we have multiple CPUs, the fast names can be different. Then all these nodes can be clubbed together into something called pools. So we'll see when we see the structure, we'll see how the pools are defined. Basically, pools are nothing but something in which we can group together the nodes. Then there's something called the resource pools as well. The resources that are assigned to the nodes can be grouped together as well for a specific purpose. There are default nodes and default node pools and default resource pools, which are just denoted by empty strings. So those are by default, a node belongs to a default node pool that is just an empty string. Then there are two kinds of resources that we can define. We can define the hard disk space and the scratch disk. The scratch disk is basically used for any temporary kind of storage of data. That is when the scratch disk will be used by all sort operators or buffer operators. When we need the data to be temporarily stored, the scratch disk will be used for that purpose. And the other disk is a hard disk for persistent storage of data. The hard disk will be used. Now this is a simple configuration file. This is how we need to define a configuration file. We define a node, and this is the format and the syntax of the configuration file. So we define a node, we give it a user-defined name. So I have the node called node1. That is a logical processing node that I have defined. Now the fast name is black hole. So that is the actual network name that is used on my system. That is the fast name. Then it belongs to pools. Now I'm just telling the in the configuration file that node 1 belongs to how many pools. By default, it belongs to, if I write an empty string, that means it belongs to the default node pool. And then I specify a particular pool that it belongs to. It's a named node pool. So I've created a specific node pool, node 1. I'm calling it node 1. Then what is the resource disk that is allocated to this node? There are two locations for the resource disk, which is the hard disk. So it datasets 1, datasets 2. Now these resource disks as well, if we see here, they are also assigned to some pools. So this is a node pool, these are resource pools. Pools empty string. Empty string means the default pool. And pools big data. So this is again a user-defined name that I have given for the resource pool. So we have called it big data. Then there's the other kind of disk space that we can define as a scratch disk for temporary storage of data. So again, there are two parts. One belongs to the default pool, the first one, and the second belongs to the sort pool. So sort is a reserved name pool. It's not a user-defined name pool. It's a reserved pool. So basically, why we need to assign them to pools is basically when we go to the data stage and we run the stage, any particular stage if we take, we have the option to constrain that in the stage editor properties. If we see, there are options to constrain that stage to run on a specific node pool. So if, for example, there is a stage that is handling a large amount of data, probably it's a join stage, and there's a large amount of data that it is joining on, that it will take more hard disk space. Some amount of data might need to be stored in the hard disk as well. Then I can constrain it to run on a pool, on a node pool, for which I have defined higher number, a greater amount of resource space. So I can constrain it to run on that node pool. So that is how in the backend data stage will decide, okay, this stage for this, I'll use this node for all the player processes to run on. So that is why we create pool if there's a particular specific requirement. Now this is a reserved name pool. This is sort. So there are some operations like sort, buffer, database, DB2 operations. These are reserved names. So if I just say sort, that means that for any sorting operation that takes place because of that stage or any of the operator, OSH operator that my data stage job gets compiled into, Any sort operation that has to take place will use this scratch disk at this location. If this gets filled up, the scratch disk gets filled up by the sort operation, then it will by default go to the default pool. But first it will go and try to use this scratch disk location space for any kind of sort operation. So for sort operation also we require a bigger scratch disk space. So probably at this location I've allocated a higher amount of space to this location. That's why I can define it as a sort pool. So similarly, the resource pools, it's basically the allocation of the disk storage. Basically, to confine how much storage we have assigned for what pool, we define all these kind of pools. We name them for a particular kind of operation, and we can then go, if we have advanced knowledge or we want to do advanced job tuning, then we can go and restrict some stages to run on particular node pools as well, or source pools as well. So by default, anytime we see a set of empty string, that means it's a default pool. And all the operators are simply stages converted into backend OSH language is operators. So all the operators will be using the default pools to run them. If there are named pools, then for particular kind of operations, or if we have constrained a stage to use that resource pool or node pool, then it will go and use that pool. So that the big data that we defined is a user defined node pool. So we have defined, so we can go to a stage, there will be an option to constrain that stage to run on a particular resource pool or a node pool. I can select it as per my requirement. The reserved name pool, the sorting operation, by default many stages have the sorting operation. We can do it on the input link when we are partitioning. So for that, we specify the sort resource pool. So sort resource pool is on the scratch disk because it will temporarily store the data for sorting it internally. It needs storage of data, temporary storage of data. So scratch disk can be used for that. So if we have defined this node pool as a sort node pool, then any sort operator will first go and try to use the scratch disk allocation. If none of that has been defined, then by default it will go to the default node pools, default resource pools. So now that was a simple configuration file with one node. Here we have got 4 nodes. In this configuration file, we have 4 nodes. The user-defined names, we can give them user-defined names. So N1, N2, N3, and N4. Those are 4 physical nodes. The fast names are also different in this case. S1, S2, S3, S4. That, sorry. That means that they're running on a cluster environment where there are multiple CPUs. Then there are pools. We have defined the pools as well as sort. So we can define the resource disk. Resources can be defined in pools. Sort pools, nodes can also be defined as sort node. So N1 is defined as sort node. And there is a resource scratch disk that is defined for the sort operator. Anything which is empty. So for a pool, when it is empty, that means it's the default pool. For any scratch disk or resource disk, a pair of brackets, curly brackets means it belongs to the default pool. So a node can belong to multiple pools, node pools. A disk can belong to, a resource disk can belong to multiple resource pools as well. So we can, this can all be defined based on how much, so this needs a lot of analysis to be done. We cannot just go and define it. We need to understand how much data we are going to handle, how much sorting would be required for that, how much buffer. So another kind of reserve name pool is the buffer. So for any buffer kind of operation, how much buffering memory do we require? Depending on that, these decisions can be taken that which pool can be allocated and specified to which named pool. So basically what as a developer we need to understand is that the number of nodes that we define here in the configuration file define the degree of parallelism that will result in a job. So the more number of jobs will mean more parallelism in the job. But that's not a shortcut, that if we want to improve the performance of the job, let's put on more nodes in the job. It has to be an optimal number of jobs, and that figure needs to be derived based on the resources that we have, how much processing capability we have, how many resources we have, how much data, what is the data volume that we are handling. So based on all those factors, it needs to be run on an optimal number of nodes. But to have any degree of parallelism in the job, we need to have at least two nodes defined in the configuration file. Because if we do not define two nodes in the configuration file, then it will be running sequentially. All the operations, all the processes will be running sequentially on a single node, which will just be like a sequential job. It will not have any degree of parallelism. To have the ability to split the partitions, split the data across partitions and the processes across different nodes, we should have minimum two nodes to run our job. So this is basically just a summary about all these things, about the configuration file. Then there's some suggestions. So there's not a clear-cut formula on how you decide how many nodes there should be defined in your configuration file. So it needs to be tested basically. It also needs to be tested at what configuration level the job is giving an optimal performance. And it will all depend on because finally the job will be running on the production environment. So it will all depend on what are the resources available in your production environment. So we can start with, if we have multiple CPUs installed in the system, the very first starting point could be that make a logical node, define a logical node for each CPU and run it for, if there are two CPUs, define two nodes and try to run the job on two nodes. But then again, mostly the jobs will be run on four nodes. So if you have two CPUs, you can have into two, you can do a into two and run it on four nodes. So you can define any number of nodes on your CPU, but at the same time, you have to see that how much hard disk you have, how much disk space can be allocated. So for that, you need to know the data volume that will be handled. So that needs to be predicted in advance. So what they give a rough estimate based on that what is the biggest size of the biggest data set size that is getting generated in any of your Datastage jobs. So we can have a number to that, if we can put a number to that. So in any Datastage, of all the Datastage jobs that will be there in the project, or even for a particular job, if we want to define it at a job level, what is the biggest volume of size of the data set that will be generated? If there are multiple data sets that are getting generated in the same job, then a sum of the sizes of all that data set into two. So that would be your temporary space that should be required. So these are some simple, these are all rough estimate formulas. There is no formula as such to come and define a number of nodes that my job needs to run on. Mostly what is done is, in the development environment, we'll be running on 2 to 4 nodes, because development environment won't have those many hard disk resources and other resources available. And then a way to test it is basically try to run a job on 2 nodes, then try to run a job on 4 nodes and see what kind of improvement we are getting in the performance. So based on that, a decision can be taken on how many nodes we need to run that job on. But then it has to be a full volume run, so that will show us the degree of parallelism. Because as you'll see, for any parallel job, there's some job startup activity also takes place. So if we try to run a job that is handling like a few thousand records only and try to run it on 4 nodes, we'll not get much improvement in performance, job run time, because there would be a large amount of overhead setup process timing that will be included in the job run time. So when we need to have a snapshot of the production volume of data, and we can test it accordingly. But mostly in development environments, it will be 2 to 4 nodes that we'll be running on. In production environments, when it's larger domain projects like retail projects, banking projects, they run up to 24 nodes, up to on configuration files which go up to 24 nodes, because there's a lot of data that is involved and they have a short batch time, so the processing needs to be finished quickly. So they run up, I have seen up to 24 nodes used in telecom domain and